Alright, today we are really going to focus, it's going to be a quick little video just on linear velocity because that was confusing to some people yesterday, so we're just going to focus on linear velocity. Now, right here, there's another formula that is in your textbook for linear velocity, and I believe you probably put S over T if you wrote that from the textbook. Now, everybody, S right here represents what's called the arc length. That's what S represents. Now, there's a formula for S, which is the arc length, that is also known as theta in radians times the radius of the circle. So theta is your angular displacement in radians, and R is the radius of your circle. So I'm going to draw a quick little circle, just so we have a circle as a reference right here. And we have a radius right here. Okay? And now angular displacement is from standard position to somewhere on that circle. So I'm just going to randomly put it right here. Call this theta. Okay? I'm not saying that this was what theta is going to be for problem number 14, but theta right here is a certain measurement, and that measurement we need to have in radians. So now we have S is equal to what? Theta times R. So if I wanted to replace this right here, I could also say V, the linear velocity, is equal to, if I substitute it, so kind of in your mind, take that and substitute it, right? What do we have? We have theta times R over what? Over time. So what we've done here, they've written it another way. So what's theta times R over time? That's the same as saying R times theta over time. These mean the exact same thing, even if I substitute that. So what I'm doing is I'm going to box in things that mean the exact same thing. Here we go. There we go. So this formula you can use. This formula right here you can also use. Now, just recently, we figured out what theta over time is equal to. What's theta over time equal to? The W, which is the angular velocity. So wait a second. What could I do with this guy right there? I could say the linear velocity is equal to the radius times, what is theta over time equal to? W, that's right, class. It's equal to W because that's what W is equal to. Time. All right, so right now, here's what I want you guys to write down. Okay? Here's all the formulas that you need to have. We'll do a quick little review. Ready? This is the first one. Put velocity equals S over T. So if you have the arc length and you divide it by time, you got the velocity. Here's another one. You can write down theta times R divided by time, or R times theta divided by time, or you can write down velocity is the radius times W. So write that down. Alright, so here we go. Now let's look at our problem. Right now, here is our problem. They've given us the linear velocity. Alright, so they've given us V. And they've given us the rate of rotation. Everybody see where it says rate of rotation? That's this guy. So they've not given us the angular velocity. What do we need to find? We need to find the angular velocity. And the angular velocity is always the radians, which is theta, over time, which we want to change our time to seconds. So right now, we need to convert this to what? We need to convert this to theta over time. So how do we do that? We took 100 revolutions in 1 minute, and we needed to convert revolutions to radians. So how much is 1 revolution in radians? What do you guys get for that? What's 1 revolution in radians? 2 pi radians. So 1 revolution is equal to 2 pi radians. Now, how many seconds are in 1 minute? 60. So that's why I'm doing some dimensional analysis here. I'm doing dimensional analysis because this revolution cancels out this revolution. This minute cancels out this minute. And all we're left with is what? Radians over seconds, which gives us our what? Our angular velocity. Not our rate of rotation, but our angular velocities. When we multiply everything in the numerator, you get 200 pi, I'd like you to label that radians, over 60 seconds. So everybody, here's what I need you guys to understand. This is W. That is the angular velocity. Okay? So watch this. Velocity equals R times W. Now this reduces, I can't help it. This reduces to 10 pi over 3. Alright? Can't leave it unsimplified, alright? I know some of you are like, oh my gosh, when's he going to simplify? Well, you know what, there it is. So there here. This is still equal to W, I just simplified. Okay? So right now, what is our V equal to in this problem? 32. What is R? We don't know. That's what actually the problem asks us to find in this particular problem. It asks us to find the radius of our circle. Okay? And what is 10 pi radians over 3 seconds equal to? That's equal to our W. So if I wanted to solve for R, if I wanted to figure out what that was, you could either divide both sides by this, or most math teachers would be really angry if I didn't do it this way. So I don't want to make anybody upset. All right? If you have a calculator, you can divide both sides by that fraction. Or you can multiply both sides by the okay? So right here, we're going to go 3 over 10 pi. And this right here, whatever that becomes, and I'll just do it in the calculator right now. I'll go parentheses. I'll hit alpha y equals enter. In the numerator, I'm going to type in a 3. In the denominator, I'm going to type a 10 and the value of pi. I'm going to close that sucker out. And what am I going to multiply that by? The number 32. And what does that give us? That gives us the length of the radius. That means R, everybody, is equal to 3.06 meters. Hopefully that clears up how to use linear velocity a little bit more than yesterday if I totally